I think we're living really in an exciting time because we have these devices that produce lots of data, and this is only going to increase even further. I mean, I can imagine autonomous devices that crawl around in the orchards with spectrometers mounted on them, and they will even produce bigger sets of data of spectra and so on that will be sent to the clouds mainly. And the challenge is then how to integrate this into the typical process flows and into, well, how to transform this into intelligence that can be used by, for example, cooperatives or by big packing houses and so on.
Hi everyone, my name is Eric Munoz and I'm an application scientist here at Felix Instruments. We're an electronics and manufacturing company that applies more than 30 years of experience into portable, field-ready instrumentation for agriculture and post-harvest applications. Our guest for today is a longtime F750 produce quality meter user from Belgium. I've had the pleasure of working with our guest in collaboration with the Flanders Center of Post-Harvest and the development of an apple harvest model. And without further ado, I present to you Dr. Bart Nicolai.
Hi, Eric.
Hi, Bart. Thanks for taking the time to chat with me today. I really appreciate it, and I believe it'll prove to be insightful for viewers at home.
Okay, pleasure.
For everyone at home, would you give us a quick introduction of who you are, your profession, and the area of your research?
Okay, so I'm a post-harvest scientist. I'm a university professor at the University of Leuven, and I'm also the executive director of the Flanders Center of Post-Harvest Technology, which is a kind of a small company that was established some years ago by the Belgian fruit and vegetable cooperatives and by the university. And the main objective was to provide like extension services to the fruit and vegetable industry here in Flanders.
Fantastic. I have a couple things that I would like to talk about today. And so we'll go ahead and get started. I'd like to give you the opportunity before we get into the Apple discussion to discuss a little bit more about the work that's done at the Flanders Center of Post-Harvest Technology. What kind of research is being done today? And then what are you most excited about currently?
Yeah, so, well, we do quite some things, but in terms of, well, we do both fruit and vegetables. In terms of fruit, the main thing that we do for or the main research that we do for the fruit and vegetable industry is to determine optimal harvest dates, which is very critical for long-term storage of palm fruit. We also determine the optimal storage conditions for palm fruit because those fruit are typically stored in controlled atmosphere conditions. We develop new storage technologies. We're very active in dynamic controlled atmosphere and stuff like that. And then in terms of vegetables, of course, those products are stored for not that long. And for example, one of the things that we do for the tomato producers is to measure all kinds of quality attributes of new tomato cultivars. Typically every year, some 50, 60 cultivars are produced by the seed houses, and before the cooperatives want to introduce them with their farmers, they want to know all kinds of features, production attributes, but also quality attributes. And based on the measurements that we will do together with productivity properties and so on, they will select cultivars that are going to produce next year. So, and then we do all kinds of we give all kinds of advice, for example, when they want to change to new refrigerants, when they want to introduce new non-destructive techniques to measure quality attributes and so on. So this is the kind of stuff that we do in the lab.
That's wonderful. It sounds like you work very closely with the farmers to be able to provide these insights. I think that's wonderful. Moving forward, I think that that's one thing that's going to change this industry, being able to use science, use technology to better improve these processes that have been around for thousands and thousands of years.
Yeah, totally agree.
For NIR applications, in your opinion, what do you think the driving force behind the exploration of NIR regarding food and agriculture is?
Well, I think it has shifted a bit. So we have been involved in NIR for quite some years. I think I had my first PhD student way back in the late 90s of last century, last millennium even, so it sounds like a long time ago. And she did a PhD on NIR applications for, well, determining like the sugar content, so the soluble solids content. We also tried different attributes like acidity and firmness and so on, but that's much more hard with just NIR reflectance or transmission spectroscopy. But we also tried to use NIR to determine the optimal harvest date of apple and pear fruit and so on. And that actually turned out to be quite successful. So throughout the years, we introduced this in practice, and we now offer for some 100 orchards every year a specific harvest advice for about 10 different cultivars and so on. And this is all based on NIR measurements. Of course, we have seen many changes. So together with NIR spectroscopy, you also have now hyperspectral imaging things, also spatially resolved spectroscopy and so on, that allow you to measure other attributes of palm fruit that are relevant, for example, for storage, like porosity measurements, things like that, and so on. But the advantage of NIR reflectance spectroscopy is, of course, that it is quite easy to do. The equipment is quite cheap. It's a very fast method. And much has changed since the advent of a diode array spectrometers that can measure in a couple of seconds a spectrum. And this also enables it to do the measurements actually in the orchard, because until now we basically did the measurements in the lab and so on, and then you need to organize the logistics of the fruit coming to the lab. But if you have like portable devices and so on, then you can go out, or you can give spectrometers to farmers or to extension specialists to go to orchards and so on, and to dramatically increase the number of data that we have. So it's becoming really a big data problem.
Yeah, definitely. What about consumer awareness? I think with NIR applications, well, the benefits are pretty clear, pretty obvious. But do you think this has reached to the consumer level where they're more aware of product waste? Is that maybe a great selling point for this type of technology?
I'm not really sure. I think, well, many people have tried. Well, you can now buy NIR measurement stations from every major sorting and grading line company and so on. And in my experience, the introduction of NIR on grading lines has been, at least in Belgium, relatively limited, and I think also in the countries around Belgium. And I think one of the reasons is that you measure properties, internal quality attributes, such as the sugar content, the soluble solids content. But the quality systems that we have in Belgium, for example, they are very traditional. They are only based so far on color and size. And then there are some offline measurements of firmness, for example, and also sugar content that in principle you should do on a batch-wise way, or in a batch-wise way to find out whether the fruit are of the highest quality and maybe can be sold under a different brand label and so on. But I think really to make progress there and to make sure that the opportunities that NIR-based measurement stations for internal quality attributes would be would be used would also mean that the quality system that we have, the grading system that we have, should be adapted to that. So to explicitly include sugar content, so that you can also do online sorting based on sugar content, which is now perfectly feasible. And I know that for some applications, like in Australia and so on, mango, and they already do it. But so far, I've not seen that many applications in this part of the world, in this part of Europe, for example. Yeah. So in terms of consumer awareness, I think maybe the main advantage would be in terms of selling fruit with a better quality. And then you will be able, or you would be able to address certain segments of consumers that are also willing to pay extra for it, because you need to make a profit after all, which means that you also need to get money to pay for the measurement station and so on. And this comes from the additional profits that you would make by selling your fruit. In terms of food losses and so on, this is of course a big issue and so on, but I'm not sure whether, at least here, this is so much of an issue, because we have a post-harvest chain, and this is not only in Belgium, the rest of Europe, and probably also in the US, that has already minimized losses to a large extent. I think most losses in countries like in Belgium and so on are rather at the level of the consumer, so not in the post-harvest chain. So yeah, that's what I think about it, at least.
Wonderful. You mentioned the large amount of data that's possible now with these in-field devices. Where do we go from here, collecting all this large amounts of data? What do you think would be the next step to be able to harness this type of power?
Yeah, I think we're living really in an exciting time because we have these devices that produce lots of data, and this is only going to increase even further. I mean, I can imagine autonomous devices that crawl around in the orchards with spectrometers mounted on them, and they will even produce bigger sets of data of spectra and so on that will be sent to the clouds mainly. And the challenge is then how to integrate this into the typical process flows, and how to transform this into intelligence that can be used by, for example, cooperatives or by big packing houses and so on. And what we see now is that many of the cooperatives and companies are developing their own big data systems because they want to use all the data that is available in their company data from sorting lines, commercial data, and so on, and to integrate the data and to extract more information from them. So the challenge, well, there are several challenges. One of the challenges is, of course, to make sure that the data that you would get, for example, from spectrometers and so on, gets into the software environment that the cooperatives, the commercial software environment that the cooperatives are now building and so on. And I think this really requires like APIs. So you have these different companies, they have different softwares for data analysis and so on. And you want to make sure, well, they will always be different, and this is even further going to increase. So you want to be sure that you get your data through some API from where you produce the data into the software of the companies. And then the next challenge is to analyze the data. So I think that some of the classical, well, we will always using the classical calibration techniques, multivariate PLS type of techniques and so on. But of course, we also see the advent and the spectacular growth of deep learning, artificial intelligence-based techniques and so on. And in order to make sense of this huge amount of data, we will need to learn how to apply these deep learning techniques to analyze the data. And then one step beyond that is, of course, to take the output of the deep learning algorithms and use these to provide advice to farmers and to commercial people and so on. And this will all be integrated in such a way that at the end you have like a very complicated and a very powerful precision or digital agriculture system where you would know from every batch of fruit or even every crate of fruit from which tree maybe they would come. And then if there's an issue, a storage issue or whatever, that you can trace it back and then to the orchard and maybe apply some precision agriculture techniques to make sure that you have maybe next year some better fertilization status or maybe better irrigation or whatever. So it perfectly fits within this general scheme of digital agriculture. And I think this is really exciting. And this is where my lab is also trying to make a difference, and many other labs in the world, by the way.
Yeah, definitely. This is very exciting. To summarize, it sounds you've outlined it where we are now able to collect this large amount of data, be able to transfer it to these data warehouses, these data lakes, and then from there, we're in the process now of being able to automate this process, being able to analyze it and do all the wonderful work that will hopefully provide insights for these farmers.
Yes, yes.
Wonderful. So I'd like to talk now about the apple model that we have been working on. And I kind of wanted to first talk about what the motivation behind creating an apple harvest application was.
The thing is that if you harvest apples too early, then apples are fruit that's ripe after harvest. So this means that if you harvest them too early, then they will never ripen. And you will provide consumers with fruit that has no taste, that is acidic, that is too firm, and so on, and maybe also small. But if you harvest too late, then you have fruit that you can't store for long term. And here in Belgium, we have some cultivars that we can store almost like year round. But then you really need to harvest at the appropriate time. And well, we actually develop different models. So there are models that we develop or have been developing to measure like sugar content of fruits. But the application that we are most interested in is to use NIR spectroscopy to determine the optimal harvest state of apple fruit and of pear fruit. This is a replacement of the traditional wet lab techniques where you would measure, like a batch of apple, you would measure the soluble source content, the acidity, the firmness, the starch state, and a bunch of other parameters and so on. But this is only possible with a lot of effort for only like 3 orchards. That's what we do. So about now we start going to the orchards, picking fruit and follow their quality attributes for the next 2 months, 2.5 months and so on. And then within a month, we start with making our own first predictions of the optimal harvest date. And so we have introduced NIR already quite a while ago, as I mentioned before, to do this in a much more efficient way. And but still, we are kind of limited because of the fruit that need to be transported to the lab and so on. So our application is really about going to the orchard, measuring or acquiring spectra with portable devices, sending the spectra to the cloud, and then run some models in the cloud, determine the optimal harvest date, and then farmers, they have these applications that run on their smartphones, and they automatically get an update of the optimal harvest date. And we improve, or the idea is to improve the prediction if you get closer to the optimal picking date. And why is it important to, besides the technical requirements, to determine the optimal, or that they know when the optimal picking date would be there? And that's because they need to organize their logistics. They need to hire labor force that typically come from the east of Europe here, because it's very difficult to find local people who still want to pick apple fruit. So it's a kind of a logistic, it solves one of their logistic problems. So this is a little bit where our application is about.
That sounds good. What are you mentioned very quickly what the traits of the model were, but could you repeat what the traits for this model are being modeled?
Yeah, so I mean, sugar content or dry mass are the attributes that you can determine quite easily with NIR spectroscopy. Several attempts have been made to measure also, or to predict also, the acidity and the firmness and so on. But that's much more difficult, and this is related to the fact that the acids in the fruits are there at a much lower concentration than the sugars. So basically, the spectrum, the reflectance spectrum, which is totally dominated by the water content, like 90% of apple, and then maybe 15%. Well, that doesn't add up anyway. Also a large amount of sugar, and then the acids are much smaller. So basically, if you look at it, the acids only produce a very small ripple on top of the spectrum. And it's actually quite difficult to extract information about the acidity from that ripple. With firmness, it's even different in the sense that firmness is a property that is, well, it's a very complex property that is related to both like the porosity, so the microstructure of the fruit, but also of the cell wand chemistry. And the cell wand chemistry changes in ways during maturation that, in chemical ways that are very difficult to measure. So there's not much that changes that you can measure actually. And this makes it quite difficult to measure the firmness. But people have tried all kinds of other properties to measure them with NIR spectroscopy. For example, one of the applications that we've worked on in the past is to measure or to predict mealiness. Mealiness is a kind of a texture disorder that is related also to the cell wall composition, but also to water status and things like that and so on. And you can take that concept further. For example, picking date is a little bit of an elusive property. It's not that easy to define it and so on. But if you can define it by a combination of different methods and so on, you can take that as a response variable, and then you basically make the NIR model or the chemometrics model between the spectra that you measure and that response variable. And you can take that even further. You could take, for example, a variable like consumer acceptability as a response variable, and that's even more elusive.
Yeah.
And it turns out that it kind of works. And that's one of the most powerful attributes of NIR spectroscopy.
Yeah, wonderful. So you're currently in your, what season is this? July just started, so you're currently collecting data. How many seasons total?
That we have done?
Yeah, that you have currently done, including this year.
Well, we started in 2000. Well, the PhD started in 97, but we started doing this commercially in 2002. So we have many seasons, like 20 seasons and so on, but not all from the same spectrometers, because we started way back with scanning grating instruments, which were very, very slow. Then we moved on to Fourier transform instruments, which were faster, but still very slow. And only then, I think, somewhere in like 2005 or 2006, we got our first diode array system and so on. And that really was a major change, because from then on, we could measure in a couple of seconds one spectrum. So this was a major step up in terms of measurement speed. But then again, also those spectrometers, after a while, they age. And then you need to, and not only the machine or the device ages, but also the software ages, in the sense that you have the software that runs on a Windows 98 computer or something like that. And at some point, there are no upgrades possible, and you have to move to a different software and so on. And that also means that you have to move to a different instrument. So every 10 years and so on, we move to a different instrument. This is now rapidly changing. Which also means that you need to develop some techniques to transfer models that you developed on earlier devices to more recent devices and so on. And then typically you would still acquire new data on the new instruments. so that after a while, the history of that old machine is forgotten, and only the new data basically make up the model. So this is the way how we work. We transfer the old model to the new machine, and gradually we acquire new data, and then a couple of years later, that transferred model or transfer model from the previous device kind of fades out, and the new data actually make up or are the basis of the new model, and so on. And then another device comes up, and then we need to do another transfer, and so on. But that kind of seems to work.
Yeah, you're sacrificing a lot of computing power by remaining on those old operating systems. And especially with the amount of data that you're collecting, this is probably going to be a huge hindrance. But so you're currently using the F750, and now actually you're using the F751 quality meters. Could you explain or talk a little bit about why you opted to use the 750 and 751 instead of multitude of options out there on the market?
So in order to increase the number of orchards that we would consider for the harvest date predictions and so on, there was no way that we were going to do this in the lab. And because the capacity we are working at full capacity in the lab, so I cannot put more staff into the lab, and there's no space anymore. So the only way to proceed was to go to the orchards using portable devices. And then we did quite a study, because there are quite some portable devices out, and for the applications that we had in mind, so both with respect to apple fruit, pear fruit, and so on, we found that the F750 was actually the best option. And in fact, we already had some experience with one of the predecessors of the F750, the Nirvana. That's an old machine, and actually you upgraded that machine to new specs to a 750, which we were very grateful for. But that's still kind of an analytical machine, so to say. So you get all bells and whistles. It's very nice to work with, and so on. But of course, it's more than what you need for applications such as our, especially when you have like fieldmen or farmers and so on that are supposed to take the spectra themselves. Then it should be very simple, and then there's also no need to pay for the extras that you have with the F750, and the F751 is considerably cheaper. And the idea now is a little bit that we either develop the model on the F750 and then transfer it to the F751, or we are also trying to do it directly on the spectra that we measure with the F751 and so on. So we're looking basically at different options and so on. But it's basically a matter of cost. So the F751 is cheaper and so on. And if we want to expand our operations to more orchards and so on, probably this would be the choice that we would make.
Yeah, definitely. I think there's probably the biggest contrast between the two instruments, because of course, at the end of the day, these devices should be used or will be used by farmers, people who not necessarily need to know exactly what the device is doing, but just the result. And so the more simple that we can make it, the better.
Yeah.
And then, of course, probably just be a cheaper instrument without all the bells and whistles of the other devices that are able to create models. Wonderful. So lastly, I just wanted to conclude by maybe talking a little bit about any prospective customers. What can you say about the devices and maybe some of the challenges that have come from using the device as well?
Well, one challenge was that when we started using the device, actually mainly the F750, Well, it was still a little bit in the development phase, which meant that, well, we had to contact the technical staff if there were some changes that we did not understand and so on. So typically things that you will encounter if you have a new device and so on. But most of these things have been ironed out now, and I'm really looking forward to this season now because we're expanding the activities, and we're also closely collaborating with our customers. So it's both the farms but also the cooperatives and so on that are very much interested in that. There's of course also a challenge. Well, at some point, we can't do it all. I mean, we cannot go to all the orchards ourselves because then I would need to hire people who are driving all the time from one orchard to the other orchard and so on. So this means that we need to also have an incentive from the cooperatives, from our customers and so on, that they also have to join us. And so far, we've had very good conversations with them, and I think something will come out of it. But they will also need to invest in time for their staff to take the spectra. You have to go to the orchards, but they do that anyway. You have to flash the fruits and then to send the data to the cloud so that we can use them. So we need their cooperation. And as I mentioned before, we also need to have access to their in-house data system. Well, we don't need to have direct access, but we need to have an access through an API so that we can interact with their system and make sure that, for example, if we predict an optimal picking date, that this information is pushed to the smartphones of their customers. And I think that the challenge now is to, first of all, convince them that they need to invest in that. And also that they have to, well, not only in terms of staff, but also money, because they will have to ask their software company to make the API so that we can have access to the in-house data warehouse systems and so on. So at the shorter term, I think these are the challenges that I can see ahead of us.
Wonderful. Last question. How close do you think you are to a finished product of this Apple model?
Well, we are already using it. So it is more like how fast can we expand it and implement it in such a way that all these farmers are connected to us via these data warehouse systems of the cooperatives and so on. And I think, well, we are doing a large trial now this year. Next year, we're probably going to further expand this and so on. But I think that we would have something that is workable at a much larger scale than we have today, maybe within like 3 years or something like that.
Wonderful. Well, I really appreciate your time, Dr. Bart Nicolai. It was a pleasure, and I hope that everyone will be able to view this episode and be able to learn quite a bit more about apples.
Okay, it was a pleasure to talk to you.